8B. Transmitting mechanical forces. 8.4. Transmitting forces. Around a corner, ideal pulleys, an ideal string, or a real one for that matter, cannot exert a force in a direction other than in line with the string. However, one of the main reasons for using a string-like connection between two systems is to exert forces on systems that are not in line with one another. The direction of tension in a string can be changed by using a pulley. Physicists employ ideal pulleys when considering theoretical systems connected by ideal strings. An ideal pulley has the following characteristics. It consists of a grooved wheel and an axle. The pulley can be mounted to a structure outside the system of interest or attached directly to the system. The axle is frictionless. The motion of the string around the wheel is frictionless. It changes the direction of the tension in the string without diminishing its magnitude. Actual mechanical systems use pulleys to change the direction of tensional forces as well, e.g., flagpoles, sailboat rigging, etc. If real systems did not use pulleys, but rather allowed a rope to wrap around an edge of a building or structural beam, for example, the rope would rapidly wear, and the force available at the end of the rope would be greatly reduced because of friction. In Figure 8-6b, FWH is the weight of the hanging block. The block exerts this force on the string, which in turn exerts a force T on the block on the tabletop. The reaction force of the tabletop block on the hanging block is T. The magnitude T prime equals FWH, but the directions are not the same. The pulley changes the direction of the transmitted force. As you will see in the following example, adjusting the orientation of the coordinate system for each object in a connected system simplifies the analysis. 8.5. Transmitting forces on inclines. It is important to realize that coordinate systems are chosen. As you have seen, the x-axis does not have to be horizontal, and the positive y-axis does not have to be opposite the direction of gravity. The only restriction is that the r-axis must be perpendicular to the y-axis. Sometimes the forces on an object will be neither horizontal nor vertical, but at an angle. In such cases, it is often helpful to define the coordinate system so that one axis is in the same direction as most of the forces. For example, Figure 8-8a shows a block sitting on an incline. Two of the forces on the block are parallel to the incline, and one force is perpendicular to the incline. Therefore, a convenient choice of coordinates would place the x-axis along the incline and the y-axis perpendicular to it, as in the free body diagram, Figure 8-8b. Figure 8-8b shows one force that is easy to overlook. That force is the normal force, N, the force exerted by the inner line on the block. This force is called the normal force because the term normal in mathematics means perpendicular to. The normal force exerted by a surface on an object in contact with it is always perpendicular to the surface. To understand the normal force, examine an object resting on a flat table. The force of the Earth's gravity on the object pulls it down. This is the object's weight, Fw. Its weight causes the object to exert a force normal to the table that is equal in magnitude and direction to the object's weight. However, this latter force is not the weight of the object. Figure 8-9 illustrates the difference between these two. Forces where Fw nom represents the normal component of the object's weight acting on the table. The table, according to Newton's third law, must exert an opposing force of equal magnitude on the object. This is the normal force, N. Therefore, the normal force can be expressed as the negative of the force exerted by the object's weight vector, perpendicular to the table. If the y-axis is vertical, N equals negative Fw norm equals negative Fwi, 8.1. If the table is tilted, as in Figure 8-10, the object's weight no longer presses fully on the table. Instead, the object exerts a force on the table equal to the magnitude of the component of its weight that is perpendicular to the incline. So the normal force decreases accordingly. 8.6. Measured weight. Weights are usually measured with spring scales or some form of electronic scale. The scale exerts an upward force that balances the object's weight. Usually, a display indicator shows the amount of force needed to balance the object's weight. For a bathroom scale, this third law reaction force is the normal force that the scale exerts on the object. In an unaccelerated reference frame, the normal force is equal in magnitude, but opposite in direction to the weight of an object resting on a horizontal surface. 8.7 Apparent weight. A spring scale is an accurate measure of weight when the scale and object are not accelerating. But what happens if they are accelerating? Note that if A is in the positive e direction, as stated in the example problem above, then MECHANICAL MGL, and the bathroom scale indicates an apparent weight greater than the weight of the box, 98.1 newtons. Will a downward acceleration give the same result? The last situation to be evaluated is the elevator dropping in freefall. Real elevators are designed to prevent this, but in this scenario, its downward acceleration would be equal to g. You probably have heard that astronauts in space are weightless. Although the force of gravity lessens with increasing distance from the Earth, astronauts are still influenced by gravity. However, their vehicle is in orbit, or free fall, around the Earth. Since the spacecraft and its occupants fall at the same rate, the astronauts seem to float. Therefore, it only appears that they have no weight. As you have seen, apparent weight equals real weight when the object being weighed is not accelerating. However, when the object is accelerating, its apparent weight is not the same as the gravitational force on the object.